So by the end of the class, you're going to be able to take the derivative of trigonometric functions. That's the goal. And we know what the trig functions are. So the basic ones are sine, cosine, and tangent. So let's start with the sine function. Look at this sine function. Sine function starts off on the x-axis at 0. The x-axis here is going up in increments of pi. So at pi over 2, it goes up to 1. At pi, it goes to 0. At 3 pi over 2, it goes to minus 1. And then it goes to 2 pi on the other side of that. All right, so we know what the sine function looks like. Now, I'm going to give you some information, and let's see if you can tell me what you think the derivative is. At the start point here, you can see the slope is positive, where I'm pointing to. That slope at 0 is actually 1. So what I've done is I put a point up here to represent what the slope is at that point. So the slope is 1. So at 0 on the x-axis, my slope is 1. At the top of the function where the function turns, you can probably figure this out. At this point here, this is pi over 2. The slope of the function, because it's a horizontal slope, the slope is actually 0. So what that means is that the point that you would have on the derivative would be pi over 2, 0, right? So the slope here at the beginning at 0 is 1. This slope here is 1. The slope at the top at its vertex, if you want to call it that, would be 0. It's flat, so it has a 0 slope. So the point pi over 2, 0 would be on its derivative. Over here, where the slope is coming down like that, or the function is coming down, the slope is actually minus 1. So I've put that in as a point. So at pi, it's minus 1. And at 3 pi over 2, where the function has a flat tangent again, that would be 3 pi over 2, 0. It's just in. And therefore, that would be another point that's on the derivative function. And then when you get back over here, it's going to be the same as the beginning of the function. At 2 pi, the slope is again 1. So there is another point on my derivative. So all of these points that you see here, so 0, 1, pi over 2, 0, pi minus 1, 3 pi over 2, 0, and 2 pi 1 are all points on the derivative function. Each of these represents the slope of the function at that point. So if you follow these points, look at these points, what would you guess is the derivative function for the sine of x? And I'll take that answer from anybody. I'd love to hear somebody tell me what they think. What do these points look like they're tracing out? What function does it look like this is tracing out right here, these dots?
Isn't it just the cos graph?
Well, look at that. You're absolutely right. It's a cos graph right there. So the derivative of the sine graph is a cos graph. You're absolutely right about that. All right, so that's your first trig derivative. Sine x is just simply cos x. That's simple. Let's have a look at the cos x graph. So this hopefully looks like the cos x graph to you, right? Starts at 1, goes to 0, then it goes to minus 1, and then it completes the cycle by the time you get to 2 pi. So the slope at 0 would be 0 because the function has a flat tangent at that point. So at 0, it's 0. At pi over 2, you have that minus 1, that decreasing line, which therefore means you have a slope of minus 1. So minus pi over 2 would be minus 1. That would be the derivative at that point, or the slope at that point, I should say. The slope at pi is going to be 0 because it's flat at that point. The slope at 3 pi over 2 would be 1 because that's increasing, and therefore the slope is 1. And at the 2 pi, the slope again flattens out, so that would be 0. So now look at these dots and ask yourself what you think the equation of this derivative line is, because these points here seem to be tracing out the derivative path of the cosine function. If you had to guess what that derivative was, looking at the way these dots are moving, what would you guess that was?
Would it be a negative sine x?
Oh, wow. Check this out. Absolutely right, minus sine x. So the derivative of the cosine function is kind of like the sine function. It's the opposite trig function, except in this case, it's actually negative. So that's what you just have to remember. Now, remember, I'm going to give you a sheet that has all these derivatives on them. So although we spent some time looking at why the derivatives are where they are, in reality, when you're looking at a test, you're going to have the sheet with all of these derivatives on them. But here's one that we can derive for ourselves. How about the tan of x? Give me some ideas as to how, I don't have a graph for this one. Give me some ideas as to how I might be able to come up with a derivative for the tan of x. Any thoughts on how we might be able to come up with that for ourselves based on what we already know? We know what the derivative of sine is. We know what the derivative of cosine is. Can that help us to find the derivative of tan? Does that help us out? What's tan? Give me another way to write tan.
Sine over cos.
Oh, okay. So we'll do that. Tan of x is the same thing as sine over cos. Perfect. So wouldn't this therefore be a quotient? And couldn't we therefore use the quotient law to come up with a derivative for tan of x? Absolutely we can. So what does that look like? Here's what it looks like. It's going to be the derivative of the top, which we already said is cosine of x, multiplied by the underived denominator. So that's just cos x, minus the derivative of the bottom, which we said is minus sine x, multiplied by the underived top, which is sine of x. So we really have cosine of x times cosine of x minus the negative sine of x, sine of x. Now, what do we call this cosine of x times cosine of x again? Remember back in the, in fact, I think you could go back to grade 11 to remember that. If I have cos x times cos x, what do we call that again? Anybody
Cos
remember?
squared.
Absolutely. So this first one is cos squared x. This one here is sine squared x. But of course, because you're minusing a minus, it's going to become plus. So it's going to be cos squared x plus sine squared x over the cos squared x. By the way, the denominator here is obviously using the quotient law, which is the denominator here squared. So it's just going to be cos squared x. So I have cos squared x plus sine squared x over cos squared x. So would I leave it like that? Is that good enough? I know you're going to say no, because you're all sharp enough to know that there is some trig identity that I can replace the cos squared x plus sine squared x is. Absolutely. And this one, by the way, over cos squared x, I should just simply write as sec squared x, because the reciprocal of cos squared is sec squared. So that's why the derivative of tan x is sec squared x. There you go. So we derived it for ourselves. Will you have this on a test? Yes, you'll have it on a test, but it's a good practice for you to know the process of going from sine x over cos x all the way to sec squared x using the derivatives. Perfect. Let's get to our first derivative of a trig function. This is 4 times sine of 5x squared. Now remember, I've said this a couple of times. If it's just a coefficient of a function, leave that out. Don't worry about that 4. Bring the 4 in at the end. So focus on only deriving the sine of 5x squared, and then you can multiply the result by 4. So we'll do that. The sine of 5x squared, now remember, it's a function of a function. It's this function, sine of the 5x squared function. So we're going to take what the sine function is as a derivative, which we just said is cosine, and just simply write that as the cosine of 5x squared, which is what this is. But then we have to multiply by the inside function. And the inside function of this is 10x. So it's the cosine of the inside function. We're not doing anything with the inside function yet. Multiplied by the derivative of the inside function, which is 10x. Everything gets multiplied by 4 because that was just a coefficient of the function. There is not much else we can do with that except combining the 10x and the 4x into 40x. So that's actually done. Let's get to the second one. Now this one is hopefully obviously a product. There's a 4x and a cosine of x. So don't think of this as just simply being a coefficient because it is a function. Right? This was just a 4, so you can think of that as a coefficient. This one is 4x. So treat this as if, no, you could treat this as if it was x cosine x and then bring the 4 in later on, but I'm just going to treat this as being 4x multiplied by cos x. So here comes my product law. Now, I'm going to take the cos of x and multiply it by the derivative of 4x, which is 4. Then I'm going to take the 4x, which is this part, and multiply it by the derivative of the cos x, which is we just said is minus sine x. I would expect you to do this for every single derivative that you're going to try to simplify it as much as possible. Factoring where factoring is possible. There's a common factor of 4 here. Let's factor it out. So it's 4 cos x minus the x sine x. That's all that is. Okay? So remember, at any point in time when I do anything which I'm going too fast on, please stop me. I can always slow down and go with whatever you're not sure about. Let's move on. So these are the first two. Here comes the next two. Sine squared 8x. And we've talked about sine squared already. What sine squared means, it's a convention that they use in math. It really means that you're taking this sine of 8x and multiplying it by itself. So I decided to write it like that so that it makes, it's sort of more obvious to you what we're about to do next. So think of this as being sine of 8x squared. It's the same thing as this. I've just written it in an unconventional way because conventionally we talk about sine squared x rather than the sine of 8x all squared. But that's really what it is. So I'm going to derive this as if this was the sine of 8x all squared. So here's what we're going to do. We're going to take this as being a function, the sine of 8x squared. Think of this as being like a u squared. That would just be therefore be 2 times the sine of 8x to the power of 1, which means that there's nothing there. Then we have to derive the inside function now. The inside function would be, instead of the sine of 8x, now becomes the cos of 8x because the derivative of sine is cos. And then we still have to multiply all of that by the derivative of that inside function. There are 3 functions happening here. There's the squared, there's the sine, and there's the 8x. And that's why you're really having to go through this like 3 times. So it's 2 times all of this to the power of 1, which is the first part here, multiplied by the derivative of the sine of 8x, which is the cos of 8x, and then multiplied by the derivative of the 8x, which is 8. So all of this is my derivative. I'm going to do this another way in a second, but I just wanted to show you that this is one answer. So there's a simplified version of the answer. The 8 and the 2 is 16, and the sine of 8x times the cos of 8x is what we had before. Now, what if we decided to think of this as the sine of 8x times the sine of 8x? So exactly what we had here before. This is something squared. So what if I just put it into 2 different functions, well, not really different, 2 of the, taking the sine of 8x times itself. That's what this is. So bear in mind, this is the same thing as this, which is the same thing as this. Well, let's do the product law this time, right? Just to see how this would work with the product law. So I'm going to take the sine of 8x, and I'm going to find the derivative of that, which is the cosine of 8x, times the derivative of the 8x, which is 8, times the underived second part, which is the sine of x. Hold on, that should have been the sine. What am I saying? Why is that just the sine? Oh, that should have been the sine of 8x. I'm sorry. I'll fix that another time. Over here, we're going to have the same thing. And really what you're going to have is this thing is going to appear twice. Okay? If you think about it, this is really going to appear twice. So it's really 2 times this thing here, right? And therefore, at the end of the day, it works out to be the same thing as what we had here before. I will make a correction here, which I'll do another time. But that represents the derivative, either when you do it by taking 2 times this and then find the root of the inside and then find the root of the inside of that, or splitting it up into sine of x times sine of 8x times sine of 8x. Okay, over here. Let's take this as another product. This is 4, again, the 4 can stay outside. I don't really need that 4 right now. I'll bring it at the end. But I'm taking the product of these 2 functions. So I'm going to take sine of 5x times the cosine of 3x as the cosine of 5x times 5, that's the derivative of this part here, multiplied by the cosine of 3x. This is not being derived yet. Then we're going to turn things around. We're going to take the cosine of 3x, which is the minus sine of 3x, that's this first part here, this second part here, multiply that by the derivative of the inside, which is the 3, multiplied by the underived first part, which is the sine of 5x. All of this, by the way, is being multiplied by 4. Hopefully that makes sense. And then I could do a little bit more than this. I could then take the, let's see what I've done here now, the 4 times the 5, which is 20, and the 4 times the 3 is, which is minus 12. Remember, there's a minus here. So that's what this represents. And well, I think that was it for that one. Let me just go back for a second here. yeah, there's nothing really much else we can do with that as well. All right, so let's move on. Look at this one. This says I'm trying to find the root of a tangent function this time. So I now have, again, -6, that's like a coefficient, the tan of this inside function here. So what I'm going to do is I'm going to treat that -6 as a coefficient, and I'm going to go ahead and call this the secant squared, that's what tan of a function is, of the 5x squared plus 4x, that inner function there. I'm going to multiply that by the derivative of the inside function, which is tan x plus 4. That's what the inside function is. And all of that's being multiplied by the -6 on the outside. So that's, the only other thing we can do with that here is do a little bit of factoring. There's a factor of this which we can pull out and put that with the -6. So the only other thing I'd say is that this would be a factor of 2 being multiplied by the -6. So the -12 times what we had before, which is the 5x plus 2, when you factor out that, and the sec squared of the 5x squared plus 4x. This is all just simply repeating what was on the previous line. And that's it for that one. There is nothing much else we can do with that. Now for this one, which is 4 over tan of 5x, I'm going to rewrite this as 4 times tan 5x to the -1. Because, yeah, we could use a quotient law, but I think that in this case, it makes more sense just to use the product of this to the -1. We're going to go with that. So we're going to treat this as if this was u to the -1, which would mean that I'd have -4 times the tan 5x to the -2 multiplied by the derivative of the inside of this now, which would be the sec squared of the 5x multiplied by the 5. All of that together represents, when you multiply these three things together, that represents the derivative of the function. We're going to have to tidy this up though, for a couple of reasons. First of all, we can put the -4 in the 5 and make that 20. Now look at the sec squared. That sec squared I'm putting on top with the 5x. This was to the power of -2. So I'm going to put that on the bottom. So this is like saying tan of 5x squared, all right? Or it's the same tan squared 5x. So that's what this represents. Now we can actually do more with this. Think back to your trig identities for a minute. Remember this, that this sec squared, well, let's think of sec for a minute. Secant is 1 over cos. Tangent is sine over cos. Right? I know you're thinking, do I really have to go through all of this? Yeah, you should. You really should. So this secant is 1 over cos. The tangent is sine over cos. So that's like saying 1 over cos times the reciprocal of this denominator, which would be cos over sine. The causes actually cancel each other out. So I'm really left with 1 over sine at the end of all of that, which is the same thing as cosecant. So what that means is that this whole, because these are both 5x, right? This is a secant squared of 5x. This is a tan squared of 5x. If I were to go through this whole process right here and simplify this to cosecant, then this becomes this, -20 cosecant squared of 5x. So unfortunately, I would expect you to do a little bit more with this when you get to this stage, when you see that they're both the same. The thing that you're finding the trig function of is the same. So there's a 5x and a 5x here. If you can manipulate the sec and the tan into a cosecant, then it makes this the result of this derivative. I hear like somebody wants to ask a question. Go right ahead. No? Okay, go ahead.
Yes. Does the tan x have to be squared for it to work?
Yes, for this, that's a very good question. It would have to be a tan squared, because if it's a sec squared, then it would have to be a tan squared as well. If this was sec squared over tan, then this would not work. Okay, but because they're both squared, or if this was just sec of 5x and tan of 5x, then you could do that. But this is squared and that is squared. They both have the same argument, 5x, and 5x. So yes, you could do more with that. That's an excellent question, by the way. Okay, so I'm gonna go to the next one. This is another tan function, a product. So that's 4 again, which is like a coefficient. The x cubed and the tan. Even though it's like a coefficient, I'm just gonna treat this like a product law question. I'm gonna derive that, which will give me the 12x squared underived tan of 5x plus the 4x cubed, not doing anything with that, times the derivative of the tan, which is the sec squared, times, no, sorry, not times, but of 5x, that's the argument on the sec squared, then that's times the derivative of the inside, which is 5. So this would be my derivative. And the only other thing I'd expect you to do with this is to factor it as much as you can. Common factor here, there's an x squared here, that's a common factor to both of them. So I'd expect you to factor that out along with the 4. So there's a 4x squared here. Then I'm going to be left with 3 tan 5x plus the 5x sec squared of 5x. Okay, so there you go. That would be the derivative of that function. And let's move on to something where we have to find a tangent equation at a particular point. So minus 6 sine of 2x. Now here's where knowing your special angles comes in handy, but you're going to have a calculator, so you don't have to memorize them. You don't have to know your special angles. You can just use your calculator. Minus 6 sine 2x. We need to find what the tangent line equation is at a particular point at x equals pi over 6. So to find a tangent line, you know you're going to have to find the slope, and then you're going to have to find the y-intercept at that point, or for that point. So let's find the slope by finding the derivative of this function first. So that would be the minus 6, the cosine of 2x times 2. Hopefully that makes sense. We've done a few of these now, so hopefully that should make sense. So there's my derivative. I know I'm going to put the pi over 6 into that. So think about what we're doing here. We're putting the cosine of 2 times pi over 6. So that's what this looks like. The function value at pi over 6 is minus 6 times the cosine of 2 times pi over 6. That's just pi over 3, by the way, when you reduce this down. So if you looked up the cosine of pi over 3, it works out to be a half. So it's minus 6 times a half times 2. And that works out to be minus 6. The half and the 2 just work out to be 1, so it works out to be minus 6. Yes, we're going to use numbers that are easy enough for you to work with. So this works out to be minus 6. This minus 6, remember, is your slope. So when x is pi over 6 on this function, the slope is minus 6. So the other thing we have to find out is what is the coordinate at that point of tangency? That's what we need to figure out now. And for that, we need to find what the y value is when we put the pi over 6 back into the original function, right? We need the x and the y. So I'm going to do that. I'm going to put the f pi over 6, put that pi over 6 into this original function. So it's minus 6 times 2 times the pi over, why do I have pi over 2 here? I don't know I have pi over 2 here. Sorry, folks. Making all these mistakes, I'll correct that later on. Anyway, this is going to be pi over 3 again, because you're going to have pi over 6 times 2, so that's going to be pi over 3. And that works out to be this. The sine of pi over 3 is root 3 over 2. So it's minus 6 times root 3 over 2. And that just reduces down to minus 3 root 3, which is what this is. All right. So this is my coordinate. At pi over 6, I'm at minus 3 root 3 when I reduce it down. So now I have my coordinate at the point of tangency. I have my slope. We know y equals mx plus b. Let's put it all together. I'm going to put the y value first is equal to the slope times the x value, pi over 6, plus b. This just works out to be minus pi. So I'm going to have this. b equals minus 3 root 3. Excuse me, 1 second. Plus pi. Okay, so if that's my b, here's my equation. So minus 6x, because that's my slope. And here's my b, minus 3 root 3 plus pi. Done. Last one. This is the last question. Nice, simple question, hopefully. I want to find the equation of the tangent of 4 tan x when x is equal to pi. This is an easy derivative because 4 tan x is just equal to 4 sec squared x. And all I need to do now is figure out what the slope is at that point, which would mean we need to know what this is. We need to put pi into that. So that's 4 over, remember what sec is. Sec is cosine, the reciprocal of cosine. So it's the cosine of pi squared. Put the 4 over the cosine of pi. That's the same thing as 4 secant squared of x. So we're talking about the cosine of pi, which is -1 squared. So that's 4 over -1 squared, which of course is just simply 4. That's my slope. That is my slope. So all I need to do now is to find the point of tangency again, the coordinate, by putting this pi back into the original equation here, right? And when I put that into the equation, it turns out that the tan of pi is 0. So it's 4 times 0, which is 0. So the point of tangency would be pi and 0, right? That's your x, that's your y. That makes it so much simpler to figure out what the equation of the line is. Because it's that 0, my y value, is equal to my slope of 4 times my x coordinate plus b. So b is -4. Sorry, -4 pi. So if I have that b, I'm ready to write my equation. Here's my equation. 4, the slope, times the x, minus the 4 pi, because that's my y-intercept. And that's it, folks. All right, that's it. That's all. That's done. Success criteria for those of you who follow that kind of thing is all there. And we're done.